My name is Niklas Fors and I will present the paper Principles and Patterns of Yastad-style reference attribute grammars. This is joint work together with Emma Söderberg and Görel Hedin from Lund University. The background for this work is a mature research tool called Yastad that is used for building compilers. It's based on attribute grammars, which allows high-level declarative implementations, and they are modular and extensible, so you can extend the compiler with new language features and new analysis. What you get is also compilers with reasonable performance if you compare to commercial tools. There are several examples of compilers written in Yastad. One is extendj, and this is an extensible Java compiler. Here, each version of the language is defined in one module, and researchers have used this compiler to extend Java with new language features and new analysis. Another example is the Optimica compiler toolkit, and this is a commercial Modelica compiler from the company Modelon. So Modelica is a language for describing dynamic systems, and these systems are described as differential equations. And what you do with that is you simulate the systems and see what happens. What we're trying to do in this paper is to document how you write compilers in Yastad. We have a tutorial that teaches people the basics, but in this work we're trying to help them more. So how do you specify compilers in Yastad? So we have identified principal patterns that people use when they write compilers, and we have then evaluated them in an empirical way by using focus groups, where we have asked 14 participants how they use Yastad. I will start by introducing attribute grammars. So this is a formalism invented in the 60s by Donald Knuth. Attribute grammars work on trees. So normally in a Yastad compiler, you have the input text, you parse it into an abstract syntax tree, and this tree is then decorated with computed properties or derived properties that we call attributes. So you might have declarations and uses, and one property or an attribute can then be the decal attribute. And this attribute points from the use to the corresponding declaration node in the tree. And another example of an attribute might be that a use have a type, and you get that from the declaration. Expressions may also have a type attribute. And we use the attributes to compute different semantic information and do type checking, code generation, and so on. The attributes are defined by declarative equations, and exactly how you do that depends on what kind of attribute it is. So there are different kinds of attributes, and Yastad supports many of them. Here are some of the attribute kinds in Yastad, and I will start with the basic ones, so synthesized and inherited attributes. So the difference is that for a synthesized attribute, the equation is defined in the node itself. For an inherited attribute, the equation is defined by an ancestor. In this example, the decal attribute here is a synthesized attribute that refers to the declaration node. But to actually find the declaration node, you need to get information from the context. And that is implemented using an inherited attribute. We also support higher order attributes, and here the value is a subtree. And this subtree can also have attributes. Parameterized attributes allow values to be sent around, and this can, for example, be used when you search for a name, and then you can pass the name to search for. Intrinsic attributes are attributes where the value is given when you construct the node or the subtree. Broadcasting is used together with inherited attributes and allows the equation to not only be defined in the parent but by any ancestor node. As you can see to the right here in the tree, we have nodes, and these nodes have types. And we allow subtyping between different kinds of node types. And we allow equation overriding so that the subtype can specialize the equation for only that node subtype. We also support attribute interfaces that can be used for reusing code between different languages. We have identified 3 principles that we use when we write compilers in Yastad. Declarative thinking is think about what to be computed rather than the computation order. So think about what attributes to be computed and then let the evaluation engine figure out the computation order. AST embedded data structures is about using the AST and, for example, reference attributes for building graphs that is superimposed on the AST. This makes the specification more extensible. Structure size specification is about using as little information about the tree structure as possible, and this also makes the specification more extensible. And this is, for example, supported by inherited attributes and broadcasting. We have identified several patterns used in Yastad compilers, and in this paper we have selected 12 of them. And they can be used, for example, for name analysis, type analysis, reification, expansion, reuse. And these patterns use different kinds of attributes, as you can see in the table. And during this presentation, I will show 4 of the patterns. So number 1, the lookup pattern, reified structure, shared compile time instantiation, and plugin component via interfaces. The first pattern is the lookup pattern, and it's about specify the name analysis in a flexible way. So we have declaration and we have uses. For example, variable names, methods, and stuff like that. So each use node has a decl attribute that will point to the declaration. And this is implemented using a inherited parameterized lookup attribute. So the lookup attribute is the attribute that actually finds the declaration. And what we pass is the name to look for, and then the equation for the lookup attribute is defined by the context, by an ancestor in the tree. In this case, it's defined by the scope node here, and the scope node defines the equation lookup so that it will search locally in the scope, and if the name is not found, then it will continue upwards in the tree. At some point you might reach the root node, and then you return some value representing that the name is not found, null or something like that. So this pattern can be used for different kinds of name analysis, like for object orientation, nested scope, and namespaces, and so on. The next pattern is reified structures, and this is about making implicit elements explicit. And we do this by using higher order attributes. So an example is that for a language we might have predefined declarations, and then we can define a higher ordered attribute that contains all the declarations. And we use this then in the lookup, that when we search for a name, we will at some point come to the root node, and then we can search in this higher order attribute and see if the name is there and return that instead. Another example is the class object in Java that you can make an higher order attribute of. The next pattern is a bit more complicated, shared compile time instantiation. And it's about instantiate a specialized variant of a definition and share it between users of the same variant. So an example is generics in Java, and you might have a list and a type parameter that is the element type. So you might have a list of integers, a list of floats. And the other part of the program you might have uses of the same kind of list. So both uses here, they use a list of integers. So they point to the same instantiation or the same higher order attribute. So this is implemented as a parameterized higher order attribute where the parameter is the variant and, for example, int or float. And the uses are reference attributes to the higher order attribute, and there are similarities between the variants, so the list of float and the list of int, so they share code. So we can also use intrinsic attributes pointing from the instantiation to the source code of the list. So that is also useful. This is the last pattern I will show, and it's plugin component via interfaces. And this is about reusing code between different languages. So Justad supports interfaces where you can have attributes and equations, and then you can let different language implement this interface, this generic component. And the specific language can then specialize the behavior by overriding certain equations, so you get a customized behavior. We are not the only one using this or some of the other patterns. And for example, this pattern has been used by Overcustoms to define name analysis. We performed an empirical evaluation using focus groups. We met 4 different groups. One group from industry that were beginners, one group that were experienced from industry, one mixed group from academia, and one experienced group from academia. And we met in total 14 participants. We did this to see if the patterns that we presented were complete in some sense and if we were missing something. And it seems that we were quite covering the patterns quite well. And this table shows which patterns they used and which pattern they want to use. So the beginners in the industry want to use some more of the patterns. We made some also observations from the focus groups. Some of them are listed here, but there are more in the paper. So it seems that the participants embraced the AST embedded data structures. It seems also that they gradually embraced the declarative thinking principles. So they start and using it more and more over time. Sometimes it happens that they have an algorithm that is specified maybe in a paper in an imperative way. And in that case, they stick to that way of describing it. It also seems that the list of patterns that we have is useful and it makes them aware of them. And it seems that the applicability of the patterns varies. So the patterns in the top are more used than the ones in the bottom. We have in this paper presented 3 principles and 12 patterns used in Justad compilers. And we hope that this will help Justad users to structure their compilers. We have performed an empirical evaluation using focus groups with 14 participants in total. We believe that the documented principle and patterns are useful and can be used in other attribute grammar systems as well, and that are used. For example, Kiama and Silver. It might be that some details are different because the systems are different. So for example, Justad is based on object orientation, Silver is based on functional programming, Kiama is a library in Scala and so on. So it might be that the details are different. But it would be very interesting to see how this relates to how compilers are written in both Kiama and Silver. Thank you very much for listening.